for 20 years. How could you make in short period of time? So I said that, yeah, I will make it in 2 years. If I could not make in 2 years, it means fail. And I don't need to have big money. Just give me 100,000 US dollars amount of money. So small money couldn't make it. It's fail. No, not working. Oh, yes, not working. Okay, thank you very much. Okay. I did not get the fund from the government anywhere, but my institution decided to support me about only 50,000 US dollars value. With that money, I made this one. It took just only 1.5 years to build one, and it was proven. And yeah, it basically it proves that it can work. And by the time I do not have any PC, so I use usual just PC with MS that is DOS program because by the time it's very hard to control the things with Windows system. So and based on that experience, humanoid robot is
KHR2. Maximum walking
it was in year 2004.
Guide walking, and humanoid robot is KHR2. Maximum walking speed is 1 point and backward walking, guide walking, and
it's working and not working alternately.
Humanoid robot is KHR2. Maximum walking speed is 1 point and backward walking, guide walking, and humanoid robot is KHR2. Maximum walking speed is 1 point and backward walking, guide walking, and
Okay. When I released this machine with very limited budgets, next year Gabon decided to me support the big money for the next one. And that was the Hubo. It was born in year 2004. So thus far, it took only 3 years to create this final version of Hubo. It is third platform from the KHR1, KHR2, and KHR3. So it does have vision system, it does have 5-finger movements, and it can walk and it can make any kind of gesture that could follow the human motion, as you see. And next year, I was requested to make very interesting, never released robot, so I decided to make this kind of Android type humanoid robot. This very famous robot named Albert Hubo, because his face looks like Albert Einstein, isn't it? And he can move his face with a very small tendon inside. He can express his emotion through his facial muscle movements. And this robot was very, very famous because it was firstly released in so-called APEC summit. So 20 world summits gathered, and it was announced on that occasion. And another interesting robot in next year was that Hubo FX1 is human carrying machine. It can carry up to 150 kilograms of freight, and it can control by joystick and by the operator. And this robot was revived 2 years ago as a named FX2. This robot is a little bit more sophisticated because it does have big arms. An arm can be controlled by a data device, so the operator could directly control the arm by through his the data device. And also, this robot was specially designed for delivering the Olympic torch during the Winter Olympic in 1.5 years ago. So this robot became very popular. In YouTube, they are everywhere. This one is the first robot who is delivering the Olympic torch, so torch relay. This one is made in year 2008, named Hubo 2. It is very light. I believe it is the world's lightest robot on this size. It weighs only 40 kilograms and very fast. It can run, it can make any kind of gestures, including sign language. If you are able to read this sign language, it means hello everybody or something. Um, and in walking, we tried early the straight knee walking. Usually, human robot use bent knee walking like this way. The reason that the human robot is always bent like this way is that this is most stable form for human also. If the ground is moving, then you naturally do like this way, because in this pose you can make any direction. You can make any direction with foot, so-called horse riding forms. So all the humanoid using that form. Without that, he has to use dynamic walking. Dynamic walking means that you always fall down, fall down, fall down, and you place your foot before fall down. That is dynamic walking. So if during the dynamic walking, someone is kick your leg, then you will fall down. But static walking, just everywhere is stable, every time stable. So that's the reason that's the most stable form in bending walking. In this dynamic walking, this the straightening walking is very dynamic, so it can save very big energy, walking energy, and also it looks more like human. And this one, the another gesture of the human, this human robot. It can pick some objects from the ground, and he can fully fold his leg, knee. Also, he can make this kind of the martial art form. And to perform this kind of movement, all the joint must be compliant. So it is using very high rate gear ratio 1 to 100. It's very position based, velocity based the actuators, but by measuring the force torque sensor in between the leg and also some inertia sensor on his chest, they stabilize hold the body. The whole robot looks very flexible and compliant. That is very, very essential to perform that. This one is kind of wild dancing, but I found that this video was just broken, so you cannot show the exact one. But I will skip this part. And this one shows how could we design the arm. The arm must be really fast. So step and go motion, poop, 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 not sine wave, just stop, go, stop, go. So to perform that one, you need very precise control is needed to perform that one. And you have to manage the reduction gear in a very effective way. Also, you have to remove heat very effectively. And we demonstrate this one. Hitting drum is not easy task for the humanoid, the robot actually, because the arm must be compliant and he should accelerate all arms from the rest position. So the hitting impact must be very strong, and after hit it must be stopped naturally, not to break himself. We tested this one when we designed the robot. So robot arm is powerful enough to hit the ball to the wall. And also we tested this kind of things. This 1-to-1 speed, no acceleration, just very naturally. This arm's weight is 3.5 kilograms, very light, and hand itself is 350 gram only. We use this kind of hands on the human robots. And also we use upper body to handle heavier materials. Actually, this project was related with Korean defense departments, and there is a prototype of robot to retrieve wounded soldier or person from the battlefield. So it is supposed to carry up to 60 kilograms. That is 60 kilograms. So it's prototype. And also it should climb up the 45-degree of the slope. So, and this model was delivered to some other countries to make their own robots. And this one is wrong. But anyhow, this ARM technology was used to develop the collaborative robot. Later I show you again, because I'll explain a little bit later this part. And also leg was tested on another way that we took the leg and we put Segway type the rolling platform down, and he tried to stabilize by himself, so he never fall down. just he can deliver a cocktail without dropping or without spilling. And also it is very compliant. And the force torque sensor mounted on just below the weight, it can amplify the external force like his exoskeleton things. And the operator can ride on this machine. It's very versatile. It's a very interesting toy for us. Expensive also. And this is a Hubo hand. So it's 5 fingers and 5 motors independently, and is tendon driven and the under-actuated, and it is shape adaptive. So once object is decided and is grabbed naturally to according to the shape of the objects. As you see that it can handle many things, and it's powerful enough. This is about 5 kilograms. It can handle 5 kilograms of the objects. And also, what else? Okay, it can even hold the chair like that way. And it weighs only 350, a little bit more than 350 kilograms, including all the actuators. Yeah, now it's watching. Yeah. And this is this wrist movement. It's 3-way movement in wrist. So making very general motion with his. And it has a force torque sensor in between the wrist, so you can detect the external force and torque, so you can make natural interaction with the human or environment. We check the strength of arm, so we ask him to make push-up, and we torch him for a moment, and he's surviving and he's doing forever. And also, we check the time to endure the battery life. So with full charge, we just keep walking, make it keep walking until it fall down. And you now see that this time 40 minutes passed. This no stopping, just continuous walking. And 1 hour and 20 minutes, still walking. And 1 or 2 hours, still walking. And 2 hours and 13, 14 minutes fall down. So it runs somewhere more than 2 hours without any stopping with a single charge. And also we check the temperature of each joint, and the delta T temperature increase is less than 5 degrees around compared with the environmental temperature. And this experiment was to DARPA Robotics Challenge. We built a next robot named DRC Hubo by the time. And as you see that all the robot, excuse me, back, okay. Touch the screen to run. Okay, as you see that the robot is very rigid, and we have to make the robot very flexible. There's 2 ways. You may have some kind of series elastic actuators or some force torque sensor in each joint, but in that case, it make the system complicated. So we did not use that kind of active torque sensor. We use only measuring current for the joint motor, and we precisely model the motor and friction, and then we compensate the gravity. Then we can make the kind of gravity zero situations, and also by that kind of technology we can experiment that kind of things. For example, say robot is supposed to drive a vehicle, then the relative distance from the robot body to steering wheel is changing like this way, but still is performing the rotation, turning the steering wheel. So he has to, like his man, we do like that thing without precise measurement of distance between body to steering wheel. He's performing that kind of thing due to the compliant control of robots. To perform that one, you have to decouple the coordinates, and you have to use the Jacobians and etc., make it work in specific directions. So for example, say in this direction, force, this direction, velocity, this direction, position, or you have to decouple that one without measuring active the force. Only we used current. That is very technical actually. And also we check the balance. So he has to be survived on that kind of external impact. And also we tested this kind of jumping on the stone. And also we tried to go over the kind of, we call rough terrain because the slope and height is not specified. He has to have a good kinematics to take care of the kind of big height and big slope without losing stability. He put each one is 5 kilograms, no, 3 kilograms. Each one like very heavy weight is on the. He simulate his arm's weight, and also he has to survive this kind of very severe disturbances on the ground. We call it blind walking. So blind walking means that robot does not have any prior knowledge about the ground. He has to survive only his tactical sensor. And also he has to be survived in rough terrain. Also, ground condition changing, stiffness changing over the grass, over the soil, over the stone, or over the concrete. And also, we are testing that kind of things. So stabilizing by stepping. So there are 3 ways to survive when it's pushed from the externally. Then one is that we call the anchor strategy. We can just basically, we use only wrinkle, and the next one is body. The hip strategy means that we can use this whole body like this way, counter moment, and third one is stepping. Now he's testing stepping things, and also we tested blind walking on that is unstable ground. I will show you again. This stone is unstable, not fixed, so it is always moving and unstable. So during on the stepping, it's changing the orientation. And these are the whole body motion, and here's view glass, and this making motion is rather easier, but it is very hard to replicate his footstep without losing stability. And also it can, oops, I run again. And so he is just following his footsteps, and it can be remotely controlled like that way. He say, hey. Okay. And this cooperative robot, we recently started. What issue when you developed this robot was that how can it remove heat effectively? So when you design this kind of humanoid robot or bipedal robot, you should have less weight on actuators and reduction gears, and you have to draw big torque from the limited size of the robot, the motor. To draw the big torque, you have to apply very high current. Then it burns the robot. So key is that how could we remove the heat effectively? Then if you can effectively remove the heat, then you can power up 3 or 4 times without burning. So that kind of thing. So we tested these heat pipes and active convection heat and fan, etc., etc. We tested to find the remove the way effectively. And also we have to make lightweight. For example, say from 3 years ago, we started to design our own motor. So we designed our own motor. We wound the coil by own way because you can buy the motor on the shelf outside, but in that case, you have to find the specification, and then you have to design your robot based upon that specification. But that limits your design. So we change the direction because you want to have better and non-existing robot. You should have your own actuator by your own specification. And then you can start to build based upon that things. So we can design all different kind of robot and the motors, and we wound by ourselves, or sometimes we invent winding machine because the coil must be densely wounded. So we invent our own winding machine and we made it. And also we design. Oh, sorry. Okay. And also we have the reduction gears. We have two types of reduction gears we've already made. A very usual planetary gear or compound planetary gear. So we don't cut, but we design, ask them to cut and reassemble. And also we have a cyclode gear. And to reduce the friction, we use very strong needle bearings inside. So we start from the 3 years, 15 years ago, we start from the scratch without any knowledge and without a budget. Now, 3 years ago, we start to build all the things, actuators and motors, reduction gears and everything. And we tested this actuator through this jumping motion. As you see that, it jumps quite high. So it draws almost 20 amperes at most. And next one. So we built the quadruped robot with these actuators. And so it is only 1 month ago. We made just 1 month ago, very new one. So it was displayed in exhibition. So people liked it. It is not jumping yet, but it will be jumping very soon, like his the cheetahs or that kind of robots. We are trying to do that in very soon. And also this is hydraulic. We started study of hydraulic systems about 3 years ago. The difficulty was that nobody knows about hydraulics because there is no hydraulic engineer in this time, because this is old technology. There is no papers. The student doesn't like to study hydraulics because how could I write the paper? Okay, without paper you cannot get a degree. So it is very hard, but I enforce my student that okay, we should make it. So we start from the scratch, nothing. We just read the text, and I design the basic things. We start to make the valve, so direct drive valve. So usually they are two-stage valve. So electric, very small electric, and some hydraulic line amplify that one, and then it moves a big cylinder. It consumes 10% of total the hydraulics. 10% means that if your pump is about, say, 10 liter per minute capacity, okay, each joint needs, for example, say 1.5 or 1 liter per minute, usual. And then each one consumes 0.1 liter per minute. But to be a humanoid robot, it should have 15 or 20 actuators. Then if you sum up, then half of them will be just used only for controlling the valve. So to prevent that kind of situation, we use direct drive. So very strong servo motor is driving the shaft directly. So it needs 80 newtons with very small, but stroke is 0.5 millimeters. So we design our own magneto-electric systems. So we built, as you see that all the cylinder, and even pump, it is the pump. We design our own motor, a pump system, and everything is merged into oil. So it just heat is naturally dissipating. And if you buy a commercial one, even in very good one, it weighs about 20 kilograms. Our is 11 kilograms. We reduce the weight because it is impossible to purchase that kind of servo valves and cylinder in the market because industrial hydraulic system is very, very heavy. So this one is used mostly for military bases, missiles or so. So it's impossible to get in commercial civil base. So that's the reason that we built this one. And we built all the parts and many failures, and we tried, and we built our own, 100% our own design. We don't buy cylinder, we don't buy the servo valve, we don't buy amplifier, we don't buy nothing, just we build. And so let's see how it moves. So we are testing the circular actuator. We have our own pressure sensor and pressure feedback. So that is very hard task. And also we made jumping leg with our own system. It jumps. We test the strength, and also we build the whole body for testing the position control and torque control. It worked. Now next one is that we making the air motion working. The strange sound is that the pump is adaptive. So pump is a feedback. So it proportionally change the rotating speed according to the hydraulic consumption. So it maximize the efficiency. Okay, and I'm in KAIST in Huber Lab, and we spinned off. We have Rainbow Robotics company, based upon the knowledge what you learned thus far, and my 5 PhD students joined in the Rainbow Robotics. We have now is 37 employees working together, and 9 out of them are PhD, and 5 out of 9 is my own PhD. So they are very much experienced in designing robots, control, and playing with robots, and we have very strong bond inside. And so we delivered a Huber robot in more than 20 places all over the world. And recently, we made, as I explained, that this collaborative robot is 100% made by Rainbow Robotics, except reduction gear. We are using harmonic drive gears, but we have motor and motor winding machine and brake and driver operating system and user UI, user interface, UX, UI, and design. We have our own designer, and what else? Everything, everything, and it's 100%. So I'm quite proud that many robot engineers production there, but there is no 100% engineer at this own. The last month we had some exhibition in Seoul. So this form of our site. I'll just show you how it's working. There are many applications. So we have 3 different sizes according to the necessity. And at last, I'll show you the last part. Oh, over there. Okay, we demonstrate cocktail machine. So it's robot is vending machine. So we're delivering the mix the different kinds of the extract and put some ice and make the things. Okay. This is the time to explain DARPA Robotics Challenge, but this time is very limited, so I have to decide go over that or skip, finish. So, but I would like to very briefly explain in 5 minutes, okay? Is it okay? Okay. Everyone knows that it does have 8 challenges. He should drive the vehicle, and he should get out from the car by himself, and he has to get into the door, open, and turn the valves and make a big hole or some sudden surprise missions and climb up the stairs and go over the rough terrain, etc., etc. The condition is that there is no decent connection. The remote control is not allowed. So once the robot is installed, then operator is located about 300 meters under the building. And there are some examiner is watching that there's no cheating because they took out all the cellular phones and cut the Wi-Fi lines. Wi-Fi line is connected, but they have scrambler inside. So they scramble the signal. So once getting, then the bandwidth of communication go to 9.6 hertz, kilohertz, 9.6 kilohertz. That is called TTL level. Just we call beaconing level. So with that kind of low bandwidth, it will take, say, 10 minutes to get the decent picture, steady picture, no dynamic picture, only steady picture. And also, the signal is scrambled and stop, and there's a switch, there is scrambles. So it's intermittently connect and disconnect, but they guarantee that it will be connected once in a minute. Very short period of time, they open full range, 100 mega bits. So on that time, you have to utilize on that time. So that's very realistic. In real disaster scene, the internet is connected, disconnected, connected, disconnected. With this, but beaconing is allowed. So we can see the condition of robot. The robot is alive or not. Okay, only see we can that one. That is very strict condition. And also, in DARPA Robot Challenge, DARPA invested 100 million US dollars for 3 years. At last, they invited three governments: Korean governments, Japanese governments, and EU headquarters. They invited us and to make it international. So Korean government decided to invest 5 million. I don't know about Japan, but they must be bigger than that. And the DARPA started from 80 million, and last they increased 20 other million, so you make 100 million, and Korean government 5 million, and some other. So total, I guess, in 120 or 30 million dollars for 3-year projects. So the government is involved, the Japanese government, Korean government, and EU government. So and as everyone knows how the money is distributed. Anyhow, I'm not going to explain that one. The whole thing is not a simple competition. It took 3 years, and we made one selection. And every time we have forum to communicate ideas, and we have test, we so-called prelim, the competition we made, and except that we brought all the machine to the United States and military base, and we demonstrate each and everybody. So it is very progressive and not just by chance. So very many communications and collaborations and communication, etc. So at last, the 25 teams were selected, and actually 9 of them are Atlas robot. Atlas robot joined 9 Atlas robots and 4 HRP. The very finest Japanese one, HRP robot. This one is. This is HRP at most right. This is HRP robot. This is Atlas, 9 Atlas, 4 this one, and Chimp. There Jackson is following of Shaft robot, and this is NASA's Robosimian. This the lunar missions, the space mission one. This is running one, and this is from the IIT, a very famous one, and make 25 teams. And the course was something like that, as you see. Everyone familiar with that. We won, and this briefly showed how it works in 20 times faster, and 19 times faster. As you see that Hubo is slid out from the vehicle. So that's very hard task, and without breaking his arm, and transformed into rolling base. Someone is cheating, but there's no rule. And open the door. So from there, the operator cannot instruct what to do. So what our strategy was that we instruct them what to do. For example, say we wait to get the one disc picture in 1 minute, and then we can analyze the situation. Then we pick that robot, go there, and get this door. We pick the points, and he transformed in 3-dimensional way. And from that, he used LiDARs and to matching the points, and he find the way by himself. So we instruct them what to do, and he has to find how to do by himself. That's our policy, the strategy. So he made big hole. And the thing happened was that this one is blocked, the way of walking. So first, the thing is he has to remove that one. So we instruct them remove that to there. So he is trying to remove that one to clear his path. And this one is very hard task because it's a sudden mission, so it is not specified before. So it must be solved by himself 100% or remotely controlled. But by himself is impossible. So we have to control it externally. The way is that it's same. We took a picture, and also with the 3D-dimensional scanning. So now in operator room, we have 3D-dimensional environment is seen, and we all simulate the motion and give the instruction in 3D-dimensional way. And the next time we send the signal, very low signal, lowest signal, and he follow. And then we check the signal again. It's very similar to space mission. In Mars, the communication time is about 20 to 1 hour, 20 minutes to 1 hour. They operate like that way. So we are doing very similar way. And another thing happened was that when it goes out from the indoor, they're very sunlight, very strong, and the eyesight is blind. So the threshold level is not adjusted. So he has very long distance. So it takes 2 or 3 minutes to adjust to recalibrate the height information from outside. This is the moment of triumph. So it's a slow video to celebrate the moment. Okay, this last step. Thank you. Backstory. That is the duality. Thank you very much.
You've shown wonderful progress in humanoid robots, and your first one in just what?
50,000.
Yeah.
Yeah.
What do you put that down to? Did you have fantastic students or fantastic technicians or fantastic industry partners?
I.
You.
Yeah. Because I'm always saying that I'm born as an engineer. So when I see the camera, I made my own. Not working, doesn't working, it doesn't matter. I want to make own. I don't like to buy. So from before elementary school boys, I made rockets, airplanes, and boats. Making boat means that not buying kit. I'm starting from the solid wood and cut and put my propellers. I make my own servo. And I made the magnets. Even my servo, I modify my walkie-talkie. It was done in early middle school. And also I made my own walkie-talkie, long-range walkie-talkie by himself, and sometimes my black powder and making rocket by himself, burn my grasses. And I made everything. I made my own telescopes and I made own mounts. And so naturally, when I see more, I make it. Because I have very many experiences in designing and playing with the sensors and playing the hardwares and gadgets and amplifiers. That is part of my hobby. So microprocessor programming and amplifier controlling, and that is my profession.
Any question from the first row? So, remarkable work that you have presented here. I have two questions. Number one, that what kind of the cooling mechanism that you have used in all types of the robots? As there are different one or for the hydraulic ones and for the humanoid robots. And number two, you have shown one robot that you have made for your defense industry. Have you ever made the robots for the defense industry that can be that can work as a fire extinguisher or that can handle the explosives?
The first question, cooling. We use air cooling, hydraulic cooling, and indirect cooling, everything. We test the hydraulic cooling, very effective, but it's bulky. So we tested with blowing, fan direct blowing, and we put very precise fin out there. And to increase the area, we sometimes use heat pipes. So we tested many things, but most effective one is that simply put some fin and put the fan. Putting fan is very effective. So passive and active is quite different. So what I learned is that if you hit it, put the fan. That's it. It solves everything. And some fan with fins. Okay. Second is that the there is no military robot actually. So the robot remote control to check the unknown things with some protection. There's so-called check the bomb or some black box unknown inside, and also some handling one mostly. Yeah, mostly handling one. But more advanced one might be drones or something. But I don't do that kind of work, and also. The human robot. There are many quests, and also that why Boston Dynamics is making human robot for military, because DARPA is sponsoring it, and all our own Korean the military the office asked me, can you make that one? Can it be used in the field? Because military robot means that not killing of people, saving our life. That's the only purpose. Nobody want to make the killing machine to save my life. That's the only purpose. So how could we save our soldier life? That's the reason that we try to replace some part. So yeah, it's possible.
I'm interested in the hands of the robot that you showed in the beginning. So you said that they're tendon activated. So the material is some sort of a wire. What's the material of that wire? And secondly, when it comes to long-term usages, what effects does it have on the tension of the wire? Does it become loose?
Yeah, exactly. A good question. The exterior material is just usual aluminum 60 and 70 series, and inside is we buy so-called wire cable, usual one, not a stainless one. The thing is that you have to purchase a so-called 7 by 19 or 4 by 17. I forgot exact number, but finer fiber, because that can allow us to use smaller diameter of the wheel, that pulley. So the diameter of pulley, ratio between diameter of pulley and the diameter of the wire, that is very critical. So we tested the 10,000 times, but about 10,000 times it become kind of small wire is getting out and start to break. So that is very critical. And losing is very clear issues. But the thing is that the losing is made by creeping long term, but also using due to the locking is released. So for our the experience, the creeping is not very critical if you made it well at first. But most critical thing is that it will be just breakdown after. It depends on the size of diameter and diameter of wire.
So my question is that as a term you suggest humanoids, humans can think. So what are the expectations that your robots in the future can think themselves and perform actions?
Okay. Actually, no answer. Thing is that what do I do research on humanoid? Because it's fun and it's very challenging. And there are so many complicated problems inside together. So it's kind of worldwide competition. But there's the Boston Dynamics, Hondas, and the ICE in Japan, and some other places in Europe, IIT, many. They're competing actually. They try to find the one place is making this one. I will make it. Everybody. It's kind of challenging. So that's the main goal. But byproduct is that we can make stronger motors, actuators, and we can test very high capacity batteries and design skills and stabilizations. That is the byproduct. And also, thirdly, people like it. If there are many robots, one humanoid, just want a humanoid robot. This is very popular. That's one important thing. And near future, it might be used for example, say in Euro Airbus company, they order to develop the humanoid to making riveting, because in airplane building you have to make rivet, but it's all the curve, so it is impossible to the point in prior. So it must be riveting during the process. So first, labor is using the rule and templates to put and make all the dots. Okay, so make sure all dots are fair, and then two persons make a whole. So, and that is very big. So there is no stairs. So there are many floors inside. So regular robot cannot register that. So they want to humanoid on the things. That is one idea.
Sir, what was the first thing you bought after winning $2 million?
All burnt, all evaporated. Mostly 90% back to the research. So yeah, we about 10% or 20% incentive to our groups, and remaining thing, and yeah, and some pay taxes.
Hello, sir. Sir,
Me?
sir.
Oh,
So-
yeah, yeah.
Sorry, sir. So really inspiring work. I'd like to ask one question. You showed the robot that walked for almost like 2 hours and 20 minutes approximately. That is quite an energy efficient design, as it has like it keep on working for such a long period of time. So which factors of the design of the humanoid will you attribute this energy efficiency to?
Okay, actually, walking composed of two things, standing and air motion. Okay, we are seeing this one is air motion. During the air motion, it doesn't need energy, because air motion, only inertia movement is enough. And standing, we steadily use the constant current to keep the shape. And another is this, we have to compensate some energy when I'm kicking down the ground. That needs torque. Okay, so if you carefully calculate the energy consumption, that is not big. So more efficient one is that you have to make mechanically frictionless and smooth and something, and also making very beautiful trajectory of movement. That is the key. The robot itself does not consume. If straightly walking, for example, by calculation, zero energy is needed. Zero energy. So if the passive walking you mentioned just before, only 3 degrees of slope, making continuous passive walking means that very few energy is consumed on walking. So if you have just plain walking, you will not be tired. You know, very small energy. You have active walk, power walking energy. So my presentation, I asked from the Hamid Jabbar that in the view of Pakistan, how could Pakistan start to the kind of advanced robot from the scratch? So I focused on that point. So I'd like to encourage you that start and make. So no complication, just start and without stopping. Okay, so continuously, and money is not a big matter actually. So you can buy the reduction gears. Each set is about $1,500. So in 10 is about, yeah, that one. Not astronomical money. So the motor is not very expensive, mostly several $100. So why? So when I make the first robot, that I claim that 100,000 is enough. The only reason is that I see the Asimo in appearance. Okay, I know what's inside. So there must be motor, reduction gears, computers, inertial sensors, force of sense. That's it. Camera. So there's no diamonds, there's no golds, there's no silver, just plain materials. So if I calculate the material cost and things, part cost, it never goes up to say 50,000. All the main thing is my own labor. And so manufacturing cost is manufacturing cost. Okay, just we can cut. If we design, they will cut. So at my first design, I use all 2-dimensional design, not 3-dimensional. I don't need to have five-axis milling machine. Just only plain 2.5 milling machine is enough to design. So designing, you can make the design by using very plain machining center. Then the manufacturing cost is not very high. So you can build your own less than say $100,000 if you have passions.
Okay. So, Professor, first of all, congratulations on leading a very inspirational and successful research program in robotics. My question would be that seeing the kind of progress that has been made in the last few years in mobility, in actuators, and all those sort of things, if you compare with the performance of animals like mountain goats that are sort of roaming around in steep hills, what do you see as the main challenge to reach that sort of capability from where you are? Is it energy? Is it actuators? Is it sensing? What is your sense?
In my view, actuator. Many people say that why don't you use artificial muscle? So they believe that there is an artificial muscle somewhere. There is no artificial muscle. So to replace that, simulate artificial muscle, somebody using hydraulics, somebody using the pneumatics, somebody is using electric motors, but far inferior than human muscle. Human muscle is just weight, especially weight is just one, just a water weight. But still 2.5 at least, average is 3 or 4. So very heavy and very small amount. So it can extract very big torque in very short period of time with this small volume, somewhere around several thousand newtons. And at the same time, it can release its power passively. So we dream that kind of actuator. So there are try to make many new emerging actuators. So artificial muscle, so-called, but not successful. Only thing actually useful is still electric, pneumatic, hydraulic. That's it. So there are ultrasonics, shape memory alloy, and the chemically activated muscles. Anything. They are only show some movement. Not, it cannot draw massive power yet.
Okay, thank you everyone. Thank you, Professor, for a very nice speech. And my name is Hamid Jabbar. I graduated from Korea. So if anyone wants to go to Korea or study in KAIS, they can contact me. I'm in Mechatronics Engineering Department. Thank you very much for your
Thank you.
participation. Thank you, Professor.